So let us now look at how regression analysis allows us to uncover the relationship between a set of variables. So let's start with a very simple example where we are trying to establish the relationship between sales and price. So in a simple regression or ordinary least squares or OLS as it is also sometimes called, there is one dependent variable y and one independent variable x. Okay, so y is a function of x. And the goal of this simple regression is to represent y as a function of x, which is also called f of x, that best fits the data. Okay, so the simplest of the functions is a line where f of x is equal to a plus b times x, where a is the intercept and b is the slope of the line. So for example, let's say y is sales and the x is price. So we are trying to estimate the relationship between sales and price. So the regression model in its simplest form assumes that sales equal a plus b times price. Now in this relationship, sales and price are data, and the unknown quantities of interest are the a and b. So the problem becomes one of finding the a and b that best fit the data. So in order to find A and B to best fit the data, we must first ask, what does it mean to best fit the data, right? What do we mean by best? So to answer this question, we need to understand some additional assumptions of the regression model. Okay, so when we are trying to estimate this relationship, sales equals A plus B times price, there is going to be some error. Okay, so note that sales equals A plus B times price is a line in the sales price space, and all we need is 2 points in this space to fit a line. So if we have more than 2 points, that is if we have 50 weeks of sales and price data, then surely if we connect any 2 points, some of the 50 points are going to be above the line and some are going to be below the line. Okay, or 48 out of 50 points will be above or below, and 2 are certainly on the line because you're joining the line by 2 points. So there's going to be some error. Okay, so the goal of the regression analysis is to find an A and B so that the error is normally distributed with a mean error of 0. That is, on average, for a given price, the estimates of A and B are such that the forecast is on average correct. Okay, so now how do we obtain such estimates of A and B, the intercept and the slope? How do we estimate that so that best fits the data and on average yield correct predictions? So let's turn to this picture. So the y-axis represents weekly sales and the x-axis the price charged. So at any point on the scatter plot, if you look at all these different points on the scatter plot, they all represent the weekly sales and the corresponding price pair. Okay, so given the sales and price data, the goal of regression analysis is to choose A and B that best fit the data. Now consider line L1. Okay, so which corresponds to the choice of A equals A1 and slope equals to B1. Slope equals B1. So with this line, if we take a price charged in any given week, that is if we take one of the x's on the scatter plot and drop a line to the x-axis, that would be the price charged in that week. Okay, so given that price, the corresponding, so essentially given that price, the forecast according to the line L1 would be sales equal A1 plus B1 times the price charged in that week. So that would be a point on the line that corresponds to that price. Okay, so let's say this is a point. So this is the price. What's the sale according to this line? According to this line, the sale is somewhere here. But the actual sale, if you notice, that's the actual sale. Okay, but the line represented sale, which was somewhere here. Okay, so the difference between the point on the line and the actual sales is the error. Okay, so note that with line L1, all the points are above the L1. So for every given price charged in that data, L1 underestimates the sales. Okay, so let us now take L2. So some of the points, so essentially some of the points are above L2 and some are below L2. Now this line has a different intercept, A2, and a different slope, P2. So in some weeks, given the prices charged A2 plus B2 times the price charged in that week equals the sales in that week. Okay, so that the sales, which is so sales price pair is on the line, but in other weeks, the prediction of sales for the price charged in that week is either above the line again or below the line. That is, if the sales price pair is above the line, then the model prediction is lower than the realized sales. And on the other hand, if the sales price is below the line, then the model prediction is higher than the realized sales. So the error is the difference between the actual sales minus the predicted sales. And this depends on the choice of A and B. Okay, so if A equals A1 and B equals B1, we get a certain error. And if A equals A2 and B equals B2, then we get a different error. Okay, so the issue is, so the other issue that is of relevance is that if we simply add up all the errors, then that might not get us to the right estimates. Why? See, when our prediction is greater than the actual, we have a positive error, right? And so when the point is above the line, we have a positive error, and when the point is below the line, we have negative errors. So if we add them all up, what are we doing? If we add up all the positives and negatives, the negatives will cancel out all the positives, right? Which would result in, again, an underestimation of the errors. However, if we choose A and B to minimize the sum of the squared errors, then we are in business, okay? So the sum of a negative error is positive, and so is the square of a negative error is positive, and so is the square of the positive error, right? So they do not sort of offset each other. And this is precisely how the estimates are obtained in regression analysis, okay? So ordinary least square is essentially a method where we are trying to minimize the sum of squared errors. Okay, so in illustration of the application of regression analysis, let's look at that. Suppose the manager wants to test the hypothesis that customers who purchase frequently also tend to purchase higher ticket items. So the conjecture here is that if we do a regression of the ticket item purchased on the frequency of purchase, we should expect a positive impact. Okay, so that's your conjecture. Now, the data that we have is on X, which represents the frequency of purchases, and Y, which represents the value of the largest dollar item purchased. So a cursory look at the data tells us that as A increases, so does Y. So the correlation between X and Y is expected to be positive. But if we were to ask, how does a unit change in frequency affect the largest dollar item, then the correlation coefficient alone just cannot help us answer that question. Okay, so that's the reason why we need to do regression. So we need to regress Y on X. So now let's suppose we regress Y on X. So we obtain the following estimates of A and B. Now these are the estimates of A and B that best fit the data or minimize the sum of squared errors. For those of you who are familiar with regression, you already know that R squared is a measure of goodness, of fit, and represents the proportion of variation in the dependent variable that is explained by the model. And R squared is bounded between 0 and 1, and the fit of the model is better the closer R squared is to 1, right? So it's between 0 and 1. The closer it is to 1, it sort of indicates the fit of the model, the better the fit is. So in this case, the R squared is actually 0.946. So almost 95% of the variance in the largest dollar item is actually explained by the frequency of purchases. So now let's turn to the interpretation of the coefficients. The intercept in general is a placeholder and does not have a sensible interpretation. Okay, so the literal interpretation of the intercept is the value of Y when X takes a value 0. Okay, but what does it really mean? So the value of the largest dollar item when the customer has never entered the store is equal to minus 18.22. I'm sure you can very well see that this does not make sense, right? So that's why there's no clean interpretation. So the coefficient of X, now the value of B, however, does have some meaning. It represents the change in Y for a unit change in X. So in this case, if the frequency was to go up by 1 unit, then all else equal, the largest dollar item purchase would increase by $10. Okay, so this is the simple regression model. This model can be easily extended to a multiple regression model by including more explanatory variables such as expenditure, advertising expenditure, the price, the advertising levels of competitors, feature, display, and so on. Okay, or promotion, and so on. You can keep adding these variables because they may all have an effect on the sales. So the coefficient of each of the explanatory variables would then capture the effect of a unit increase in that variable, all else being equal. So the regression model therefore allows us to create a forecasting tool by allowing us to relate an outcome variable of interest, so the dependent variables like sale, with multiple explanatory variables, and once the estimates are obtained, then we can forecast the outcome of variables of interest at different values of the explanatory variables. Okay. So let me now turn to a data reduction technique that can be used to construct perceptual maps using survey data. Now, in this survey, the respondents were asked to rate each of the 5 stores on a scale of 1 to 10 on a variety of questions. So the 5 stores in the study were Marshall, Lord and Taylor, JCPenney, TJ Maxx, okay, so and so on. So the goal of the study was much larger, in that we are interested in whether the promotional policies of high-end stores such as Marshall Field and Lord and Taylor were systematically different from those of the other stores. So now the survey that I show here is a subset of a much larger survey. As I mentioned earlier, surveys are typically designed by conducting a focus group with a few customers in the target audience. Now, during the focus group, the store's decor, the ambiance, and the convenience of shopping at the store came up repeatedly and seemed to be a salient factor that influenced store choice and the shopping behavior of consumers. So consequently, we framed the questions to related to convenience and ambiance, and had the respondents, each of the 5 respondents respond to each of the 5 stores on the 10 questions. Okay, so each customer would rate Marshall Field on these 10 questions and then take another sheet and rate Lord and Taylor and so on. So if you look at the questions carefully, you will see that there were several questions that attempt to capture consumers' perceptions of convenience of shopping at the store, and another set that attempts to get their views on the decor, ambiance, and organization of the store. So for instance, question 1, 2, 6, and 7 are related to convenience, and the other questions are related to the store organization and ambiance, etc. Now, we might ask, why do we have duplication in the survey? So in other words, why do we need to ask 4 questions related to convenience? Why could we simply not have asked 1 question and just be done? So the answer is, we want to ensure that the respondents are reliable. We want to ensure that the respondent is not randomly selecting the responses. So if the same question is framed differently, then it's possible to verify whether the consumer's responses across the questions are consistent or not. Okay. So what I mean by that is, if the consumer responds to question 1 and claims that it's a convenient place to shop, then responds to question 2 by indicating that the store has a slow checkout, then these 2 responses are not consistent, right? So they're inconsistent. So on one hand, we need to have a set of multiple questions on the same underlying construct framed differently to verify the reliability of the consumer response. And on the other hand, this comes at the expense of redundancy. Okay, so there are multiple questions or variables which do not have unique information. So for instance, if a consumer is consistent in their responses, then their responses to the questions of 1, 2, 6, and 7 should be highly correlated, right? And their responses to the other set of questions related to decor and ambiance of the store should also be highly correlated. Now, there is a data reduction technique which exploits the correlation structure among the variables and uncovers the underlying latent constructs or factors. Now, each of the factors is expressed as a linear combination of the responses to the 10 questions. So there are ways to determine how many factors to retain with minimal loss of information in the data on the 10 questions, and how to label or determine what are the factors, what the factors represent, etc., which is really beyond the scope of this class. But for our purpose, let us say we perform factor analysis and we obtain 2 factors, each a weighted sum of the responses to the 10 questions. Then we have a simple formula that allows us to obtain values of factor 1 and factor 2 given the responses to the 10 questions. That is, we can obtain factor 1 and factor 2 values for each of the 5 stores for every customer. Suppose factor 1 is convenience and factor 2 is ambiance. So we can now pick a store, say Lord and Taylor, and compute the average value of convenience and ambience across all consumers. We can then take Marshall Fields and do the same. That is, we can obtain the average perception of the customer on convenience and ambience for each of the 5 stores. And then we can plot these 5 points on in the convenience ambient space to essentially obtain the perceptual map, which, as we saw in our product session, offers very, very useful insights on how differentiated we are perceived to be from the competition. Okay, so who's our closest competitor? Where are we doing head-to-head positioning? Where are we doing differentiation positioning? Where are the holes? Okay, so what actions we could take to further differentiate ourselves from the competition or be perceived to be closer substitute of a specific competitor, or whether or not there is a need for us to reposition ourselves completely. Okay, so these are the key implications. Now, before we conclude the session, I want to discuss another application of surveys, which is to estimate the market potential. Okay, so one approach to estimating market potential is by conducting purchase intention surveys in which the consumer is presented with a description of the product offering and asked explicitly to state how likely they are to purchase the product. If the customer says, for example, that they're 80% likely to purchase it, and if the survey is conducted over a sample that represents the target audience, then we can extrapolate the average purchase probability obtained from the survey responses to the set of buyers in the target audience to get an estimate of the potential demand. Okay. However, because there is a potential of what is called a demand effect in purchase intention surveys, which is the idea that when you ask respondents in a survey to explicitly state their purchase intention or attitudes towards the brand, well, they tend to overstate the purchase intention, because a lot of times you don't get the right answers. So that's really the issue. Now, it's helpful, therefore, to deflate the estimates that we obtain to get a more conservative or realistic estimate of the demand potential. So it's not uncommon to deflate the estimates by a factor or two to get a conservative estimate of the number of potential buyers. So once we obtain an estimate of the number of potential buyers in this manner, we can then multiply it with the average purchase rate to obtain an estimate of the market potential. So I want to conclude the session by saying that this is one approach to estimating demand potential. In more established mature markets where there is historically purchased data, we could apply several quantitative tools to estimate demand potential. All right, so with that, I'll end the session and thank you for listening.